Hello, welcome back to another video on vectors. Today we'll be covering the second part of this topic, which will cover all the essential problem-solving strategies you'll need to ace this topic and to tackle challenging questions that can come out in the H2 exam. So this is an example of a type 2 question. So as you can see, all these questions have lots of numerical values and require a lot of application. So these are what we call application questions, or questions that require a lot of problem-solving strategies. So type 2 questions can actually be all classified as interactions between these three components in vector geometry. So this would be the point, the line, and the plane. So in the previous video, we learned about how to represent a point in the vector space, and we also learned about the three different equations of a line and three different equations for the plane. Okay, so this is how we'll be discussing problem-solving strategies today. We'll actually be breaking it up into 6 different categories, starting with any question that involves a point and another point. So after we finish this, we'll move on to point and line, so on and so forth. So don't worry if this doesn't make much sense to you now, it will slowly make more sense. Okay, so we'll first start with part A, point and point. So what we mean by point and point is given any 2 points, say point A with a positional vector x, y, z. So let's say our point A is over here, positional vector x, y, z. And another point B with positional vector a, b, c. If we draw the vector from point B to point A, so look like this, this is actually equals to OA minus OB. So do note that when we are expressing a vector as the two positional vectors subtracted from each other, we always start with the letter on the second letter, OA, and then we do the first letter. So it's kind of like reversing the vector, okay? So we take the positional vector A minus the positional vector B in order to get x minus A, y minus B, and z minus C. And next, if you want to find the distance between the 2 points, it would simply be finding the magnitude or the modulus of this vector, which by Pythagoras theorem would be equals to x minus a squared plus y minus b squared plus z minus c squared. And last but not least, they can ask you for the equation of the line passing through the 2 points. So first, we need to pick any point, x, y, z, or a, b, c, and this would come in here, plus lambda multiplied by a vector that is parallel to the line passing through a and b. So this can just be the vector that connects a and b, which we found here, x minus a, y minus b, and z minus c. Here lambda can be any real constant. So if you say you sub in lambda equals 1 or minus 2 or 4, for example, you get different possible vectors for r, right? And each value for r would correspond to a unique point on the line. Okay, so that's actually all for all the questions they can test about interactions between one point and another point. So next we'll be moving on to the interactions between a point and a line. Alright, so firstly, we define a point A, as we see over here, point A, and a line L. So the line, a straight line here with vector equation r equals to b plus mu c. Okay, so the first kind of question they can ask is if the point lies on the line. So if the point lies on the line, then the positional vector A would be able to fit into r over here. So we can write it as A equals to b plus mu c. So all we have to do is check whether this equation is satisfiable. So in order to do that, we just need to bring b over, and we write a minus b, and we just check that it is a scalar multiple of c. Okay, so why this is true is, say we have a point b over here, lying on the line already. If we want to show that a lies on the line as well, say it's here, all we have to do is show that AB is perpendicular to the directional vector c, right? And since b is already a point lying on the line, if you can show that AB is parallel to c, or in other words, it's a scalar multiple, this would mean that A lies on the line as well. So if you can extend the line, it will look like this. Okay, so next, moving on, the next kind of question they can ask us about a point and a line would be the foot of the perpendicular from the point to the line. So same, we define a point A and the line L defined by this vector equation. And we want to find the foot of the perpendicular, which means drawing a 90-degree angle over here from the point to this line. So what we do is we realize that first the foot of the perpendicular must satisfy this vector equation as well. So D equals to B plus lambda C. And next what we do is we use this and we subtract it with the positional vector of A minus D, in order to get this vector over here. This is our A minus D. Okay? And after we get this vector, all we have to do is dot it with the vector that defines this line, or is parallel to this line, which will be vector C. And all we have to do is take A minus D and dot it with C, since we know that the dot product of two perpendicular vectors must be equals to 0. And after you do this, you'll be able to solve for lambda. And after you solve for lambda, you just sub it back in over here, and you can get the positional vector of D. Okay, the last kind of question they can ask is something similar to the previous one, but instead of asking for the perpendicular, foot of perpendicular, they go one step further. So here they are asking for the shortest or perpendicular distance. So they're asking for this distance over here. So the easiest way and the most direct way would just be to find the foot of perpendicular first, and then use your magnitude formula, the one that looks like this, in order to find the length of this shortest distance from a point to a line. But there is actually a faster method to do so. So we can actually use cross product, okay? So let's say we have a point here and a line, okay? So let's say this line is defined by the vector B that is parallel here. And let's say we have our point A here. All we have to do is find a point lying on the line as well. So let's say this point is, let's say, X, okay? And we call this vector here A. So what we have to do, we want to find this length, right? All we have to do is take the modulus of vector A cross with the unit vector of B. So let's say B is 3, 4, and 5. Then the unit vector of B will be equals to 3 over square root 50, 4 over square root 50, and 5 over square root 50. And all we have to do is take this vector right here and cross it with the unit vector over here, and then find the magnitude. This is a way faster way to get the perpendicular distance from a point to a line. And this is actually a quotable theorem. So you can use this in the exam to simplify your working. Okay? So now we are done covering the 3 different types of interactions between a point and a line. And next we'll move on to line versus line. So we talk about two lines, L and M. Just now we're talking about a point and a line, right? Now instead of a point, we have another line. So this other line has a vector equation r equals to c plus mu d, and the line L has r equals to a plus lambda b. So questions will typically ask whether the two lines intersect. Intersect meaning they cross, or if they are parallel, which means they don't cross, or skewed. Skewed means they will never ever touch each other as well. But they're not parallel, okay? But they're not parallel. So these are the 3 types of maybe something like this and I'm not sure how to draw a pair of skewed lines. Maybe something like this. Okay, these lines aren't exactly parallel, but they may be lying on different planes, so they will never meet. Okay, so these are the kinds of relations they can ask between two lines. So if two lines are parallel, firstly, then their directional vectors B and D would be parallel to each other. In this case, the vectors B and D would then be scalar multiples of each other. So you can write B equals to, say, KD. Okay? So this is how we can tell if two vectors are parallel. Next, if we have already eliminated the possibility of two lines being parallel, we can try and see if the two lines intersect. So all we have to do to see if two lines intersect is to equate these two equations together. And then we solve. So we know that each vector here will have 3 terms, right? So let's say C is 1, 2, 3, and say our D is, say, 4, 5, 6. Okay, and let's say our A over here is say 2, 3, and 4. And our lambda here is 1, say 2, and maybe 5 over 2. Okay? So now we equate these lines together, and we want to see if they intersect. So we want to see if we can find values of mu and lambda that satisfies this entire relation. Now if we realize we try 1 here and 2, we'll be able to check the system of all 3 equations that we get. The first one is 1 plus 4 mu equals to 2 plus lambda, right? 2 plus 2 lambda. No, 2 plus lambda, sorry. And here we have 2 plus 5 mu equals to 3 plus 2 lambda. And 3 plus 6 mu equals to 4 plus 5 over 2 lambda. So we actually get a system of 3 separate linear equations, each with 2 variables. So we need to be able to find values of mu and lambda that satisfies all 3 set of equations. Satisfying 2 only is not enough, okay? It has to satisfy all 3 equations. So here we happen to find the values of mu and lambda that work, so 1 and 2. So 1 plus 1 times 4 is equals to 2 plus 2 times 1, so on and so forth. Remember, it must work for every single row, okay? So if you are able to find values that work, usually we use the GC. So if you're able to find values that work, then we know that the 2 lines do intersect at a point. Okay, so this is actually what we were talking about just now. So we use the GC to solve the simultaneous equation for all 3 equations in 2 variables, okay? It has to satisfy all 3 equations. So going back to just now that we found 2 values of mu and lambda that work, the value of the positional vector of the point of intersection would just be taking any of these and calculating the vector. So 1 plus 1 times 4 will give you 5, 2 plus 1 times 5 will give you 7, and 3 plus 1 times 6 gives you 9. So 5, 7, 9 would be a common point of the point of intersection between the 2 lines that we have here. Okay? So if the 2 lines are intersecting, they can ask for the angle between the 2 lines. So let's say we have 2 lines defined by, say this is vector B and this is parallel to vector C. We can actually find the angle in between these 2 vectors. And this can be achieved by using the dot product formula. Sorry, let's use D over here. B dot D equals to magnitude of B, magnitude of D, cosine theta. So all we have to do is divide both sides by this quantity right here, and we can rearrange it to find cosine theta equals to this. Okay, so now what happens if we have 2 lines and we want to find this acute angle, and the angle we get from this equation is obtuse? Then that can't be correct, right? If we obviously want this acute angle. But if you realize the angle between the 2 vectors is slightly vague because it can mean this angle as well. So you just need to take 180 minus your answer to get what you want. But if you already get an acute value, then usually there's no need to do that. Okay, so next, if the 2 lines are parallel, one of the things they can ask you to do is find the distance between the 2 lines. So in order to do this, we just have to find any point on the first line and do what we did before, which is find the perpendicular distance between this line and the other line. So we can do that by either using the cross product rule, which would be A, remember this, A cross the unit vector of B, or we can just find the foot of perpendicular and then use Pythagoras theorem to find the shortest distance. Okay, so if the 2 lines are skewed, which means they never ever intersect and aren't parallel as well, they can't really ask anything about this. So usually they'll just ask whether the 2 lines are skewed, and they won't be asking like where distance between the 2 lines or anything. So there's nothing they can ask. Okay, so next we're going to talk about the length of projection of a vector on a line. So the length of projection is kind of like a shadow. You can think of it as a shadow. So say we have this vector A over here, and we have a line here. So you can think of it as a light shining from the top. The length of projection, if you draw the perpendicular here, this is the length of projection. Okay, so remember just now we defined this as the B. This is our B here, and our perpendicular distance here, perpendicular, right, was equals to A cross the unit vector of B. So in order to find the length of projection, the formula is almost exactly the same. but now you just do A dot the unit vector of B instead. So you can remember in a very simple way. So basically, if you want to find the length of projection, you dot the unit vector along this line. And if you want to find the perpendicular distance, which is the so-called the other length, and it's not along this line, then you'll be crossing B, the unit vector of B. Okay, so A dot unit vector of B and A cross unit vector of B. Okay, so now we can use dot product. Okay, so this was actually mentioned in the previous slide. So I've already illustrated it on the same diagram as shown over here. So the length of projection here for this vector right here is A dot the unit vector of B. And the perpendicular height here is A cross the unit vector of B. Okay, so now we've completed all possible interactions between a line and another line. So next we'll be moving on to the most challenging kinds of interactions when planes come in. So we first start off with points and planes. And for this part from this part onwards, we'll be using numerical examples to illustrate each of these interactions and make it clearer to you. So for point and plane, the first question they can ask is, does the point lie on the plane? So let's say we are given a point 0, 0, 7. So let's say our A is equals to 0, 0, 7. And the equation of our plane is, let's say, r dot 3, 4, 5 equals to 35. So the normal vector here would be the vector that is perpendicular to the plane. So this is our normal vector equals to 3, 4, 5. So if you want to check if this point lies on the plane, all we have to do is sub it into r. Because we know that if it does lie on the plane, then one of the values of r has to be 0, 0, 7. So all we have to do is check that 0, 0, 7 dot 3, 4, 5 is equals to 35. And this is true because 0 times 3 is 0, 0 times 4 is 0, and 7 times 5 is 35. So if we add it up all together, we get 35. So since we've verified that it fits this equation, we know that the point 0, 0, 7 does indeed lie on the plane. Okay, so the next kind of question they can ask is to find the foot of the perpendicular, just like a line, but instead of finding a foot of perpendicular from the point to the plane, to the line, we are now doing it from the point to the plane. So as usual, we consider the exact same plane, r dot 3, 4, 5 equals to 35 over here, and we are using the same point. Let's say we consider a different point now. We want to consider the point 4, minus 3, and minus 3. So what can we do here? So we know that the equation, the vector representing the normal, is equals to 3, 4, 5, right? So if we were to find the equation, or the positional vector of this point B, it must kind of lie on the same line that connects A, B. So what is the equation of the line that passes through A and B? So the equation of the line will simply be r equals to 4 minus 3 plus, say, lambda multiplied by the normal 3, 4, 5, because this line is parallel to the normal, because it's the foot of the perpendicular, right? So our point B has to be in this form over here. So for convenience sake, let's just use the same constant lambda again. Okay, so our point B is represented as lambda times our normal vector 3, 4, 5 plus 8. So this is our numerical example over here. And all we have to do after we get this point is sub it back into this dot product, and we will be getting our answer. So if I'm not wrong, we have another slide over here. So 4 minus 3 plus lambda 3, 4, 5. We take this entire thing and dot it with the normal, and we should get 35. So if we expand this out, we can use the distributive law to expand the dot product. So we start with this dot with this, which we get minus 15. Okay, plus lambda times this dotted with this, which gives us 9, 16, 25. So that's 50 equals to 35. And a bit of rearrangement will tell us that the value of lambda is equals to 1. So now all we have to do is because remember this is our positional vector for B. Now we just have to sub in the value of lambda in again. So our positional vector OB would just be equals to 4 minus 3 minus 3 plus 1 times this vector, so we don't have to write the 1. 3, 4, 5. And now our positional vector for B will be 7, 1, and 2. Alright, so that's how we find the foot of perpendicular from a point to a plane. And lastly, the last kind of question they can ask is the distance between the point and the plane. So this is simple. If you already have the positional vector of the foot of perpendicular, if you already have the foot of perpendicular here, right? So all you have to do is use Pythagoras theorem to find the distance, just like for between point and line. Okay, and another method you can actually use, right, is because usually finding the point on the plane itself that is perpendicular is very difficult. And if the question doesn't even require you to use foot of perpendicular or to find the foot of perpendicular, this can usually take a lot of steps. So what we can do is actually find another point, let's say a point C, and we take this vector over here, call this vector, let's say, let's call it X, okay? And we look at this vector right here, and let's call it, let's say, Y. So if we draw it out again, it will look very similar to what we were doing with length of projection just now, right? Where we have a vector Y over here, a vector X over here, and we want to find the length of projection, which here becomes the perpendicular distance. But if you look at this angle here and this angle here, they are the same, right? So we can kind of flip it around mentally, and all we have to do now is take X dot the unit vector of Y, and your unit vector of Y here is actually equals to your normal, so we can replace this Y with normal because this is parallel to the normal vector, and this alone will be able to give us the length of the length from A to the plane, right? The length from the point to the plane. So this is actually a shortcut method to find the distance between the point and the plane. And last but not least, we actually have this really fast formula, and I'll be explaining this formula in greater detail when we talk about the interaction between planes and planes. But this theorem over here cannot be quoted directly. So what you have to do is actually you have to mention that there is a plane passing through point A, which is why we have this A dot n term over here. But if you don't understand this, it's completely fine. We'll be making sense of it to you later when we explain interactions between a plane and another plane. Okay, so for now, just stick to either the dot product method or using the elementary method, which is finding the distance between the foot of perpendicular and the point. Okay, so now that we've completed the interactions between a point and a plane, we are left with line plane and plane plane. So let's talk about the interactions between a line and a plane. So the first question they can ask is whether the line is parallel to the plane. So in order to do this, we recall that every plane has a normal vector. So all we have to do is, here is parallel to B, right? We just have to check if B dot n equals to 0. Because if B dot n equals to 0, this would mean that B is perpendicular to n. And since the normal is perpendicular to the plane, so the line will be perpendicular, the line will be parallel to the plane also. Okay, so now what happens if the line lies on the plane is that basically, this point here will be able to fit into the R over here. And we can also use it in our vector equation, okay? So next, moving on to, if the line is parallel to a plane, another follow-up question they can ask is, what's the distance between the line and the plane? So what you can do is just pick any point on the line and calculate the distance to the plane, like what we taught just now between a point and a plane. So we realize that a lot of interactions between line and plane are the same as point and line and point and plane. We are just picking a point on the line and doing the exact same thing that we did before. So when we see questions, we actually just have to identify what they're asking for, because more often than not, there's only one or two standard methods that you can use to solve every single kind of question. Okay, so if the line is not parallel to the plane, they will definitely intersect, right? So they can ask, so they're likely to intersect, sorry. So the first thing they can ask is the point of intersection between this line and the plane. So this line over here, a plus lambda b, must be able to have a point that satisfies this r over here. So let's say this point happens to be a plus lambda b. Okay? So we take a plus lambda b and we throw it into the equation for a plane. And when we dot it with the normal vector, we should get d here as well. And after we get this, we can just plug it back into the vector equation and find the point of intersection. Okay, so the second thing here is actually the angle between the line and the plane. So we know that this angle here, right? This angle over here, we want to find the angle between the length and the plane. And if we draw the normal vector over here, we realize that this angle actually equals to 90 degrees minus this angle over here. And we know that since we have the vector for this and the vector for the normal, we can use the cosine formula. Cosine theta equals to b dot n over bn, like so. And we can find the angle here, and we just take 90 minus the angle to get the angle between the line and the plane. Okay? So last but not least, they can ask for the length of projection of this vector b onto the plane. So what we do is instead we can take this as so-called like our base. So we look at it like this, n and our b. And instead, now we want to find this distance, right? So instead of looking at it as the length of projection, we look at it as the perpendicular distance. So we just use the cross product formula as we learned just now. How do I move this away? Okay, so we just use the cross product formula. B cross unit vector of normal will give us this perpendicular distance. Okay, so now we're going to move on to the final kind of interaction, which is often also the most challenging. So we'll be talking about two planes interacting with each other. So a problem involving the interaction between planes will either have two planes or three planes. No more, no less. So in dealing with two planes, the first question is whether they are parallel. So how we figure this out is, all we have to do is take the normal vector. Let's say this is n1 and this is n2. We take a normal vector over here, n2. And we just have to show that n1 and n2 are parallel to each other. And in order to do that, we just have to show that they are scalar multiples of each other. So when dealing with two parallel planes, it always helps to use the same normal vector. Because we know the normal vectors 1, 2, 3, 2, 4, 6, 3, 6, 9, these are all the same normal vector. Because the normal vector isn't a unit vector. It just has to be a vector that is parallel to the normal, right? But when we are dealing with two parallel planes, it always helps to just pick one and use it for the two parallel planes. So for example, r dot 1, 2, 3 equals to 7. This could be the equation of our first plane. And for the second plane, we could have r dot, say, 1, 2, 3 equals to maybe 13. So it really helps if we write the same normal vector, so it allows us to compare things easier. And you'll actually learn why later. Okay, so the next question they can ask you is the distance between the two planes. So if you write it in the same format like this, right? We have to have the same normal, okay? And these are two parallel planes. The shortcut for finding the distance between the two planes would just be to take E minus D, or D minus E for this formula's sake, and divide it by the magnitude of the normal vector. And this would just immediately give us the distance between two planes. And if you realize that this is the same as the very complicated looking formula just now where we had a point A, and we wanted to find the perpendicular distance from this point to the plane over here, we see that this formula D minus E is the same as D minus A dot N, because we learned that the equation of the plane is R dot N equals to E equals to A dot N, because A is a point lying on the plane in the first place, right? So this is the formula that you can use for the distance between a point and a plane. And this is the formula for the distance between two planes. But do note that, as mentioned earlier, you see here, we have to use the exact same normal vector. We can't be using 2, 4, 6 here and 1, 2, 3. We have to pick the same normal vector and use it. Okay, so this is a highly suggested method to use for point and plane as it really shortens things and shortens your working. Okay, so if the two planes are not parallel, they will intersect on a line. So you see we have a plane here and we have a plane here. They intersect at a line. So how do we find the equation for this line? So first let's talk about how do we find the angle of intersection of these two planes. So it will be something like this angle. So to find the angle of intersection between the two planes, we cannot just take the two planes directly and do some operation on it. It doesn't work. So what we have to do is work with their normals. Because the angle between the two normals is the same as the angle between the two planes. If you think about it like this, say our two planes are like this. Okay, we want to find this angle. If you draw the two normals over here, okay, it's supposed to be 3D, so it's a bit hard to see, but this angle, the angle between the two normals, right, will actually be equals to the angle between the two planes. And we can find this using the dot product between the two normals, so using the cosine formula just as before. So the next thing they can ask is to find the line of intersection between the two planes. So what we do, right, is we look at the Cartesian equations of the two planes. So let's say our first plane is equation like this. So this will have a Cartesian equation 0x plus y plus 2z equals to 7. And let's say we have another one, r dot 3, 4, 5 equals to 35. We will get the equation 3x plus 4y plus 5z equals to 35. Now we see that we have two equations and three unknown variables. So we key this into polysimult function in our calculator to solve two linear equations and three variables, and our output will look something like this. x1 equals to 7,3 plus x3, x2 equals to 7 minus 2x3, and x3 equals to x3. So here, x1, x2, x3 is just the calculator's way of saying x, y, and z. So basically what it means is you can pick any value of x3. Let's say we pick x3 to be 0. If we pick x3 to be 0, then our x value will be equals to 7 over 3 plus x over 3, right, which is 7 over 3. And our y value will be 7. But instead of finding the values x, y, and z, right, there's actually an even shorter method. So if we look at this and this, right, we look at the constants. Okay, so the constants before the x3. So before x3, there's nothing, so it's 0 plus. We just copy these. We copy 7 over 3, 7, 0. And this is a point line on the line of intersection, right? Just now when I explained when we sub in x3 equals 0. And next, we just add lambda. You look at the coefficient of x3, 1. Coefficient of x3, minus 2. And coefficient of x3, 1. This is the equation for our line. Isn't this a lot simpler? So if we substitute different values of lambda, here your lambda is basically your x3. So when you sub in different values of lambda, you'll get different points that lie on the line, but this is the fastest and quickest way to find the line of intersection between two planes. Just look at what the calculator outputs you and copy it out in this form. Okay? So next, sometimes this may not be possible, so the question may guide you to find a point on the common line first. So let's say we already have a point on the line, right? And they ask you to use hence find the equation of the line that is the line of intersection between the two planes. So now what you do is you find the directional vector of this line, which can also be found via the cross product of the two normal vectors. So let's say we have two planes, okay, intersecting here. If we find the normal vector of n1 and n2, the resultant may look something like this. The resultant, let's say B prime. So this thing that we get from crossing n1 and n2 will give us a vector that is parallel to the line of intersection between the two planes. So then we can just write our equation as r equals to point. So this point is the one that you got earlier in the question, plus lambda b. So the last thing they can ask you is the intersection of three planes. So they may actually end up in many different situations. So you can pause a while to look at the different kinds of situations that three planes can intersect in. But this is very uncommon, and usually the more common ones would be this and this one. And if they intersect all at one point, okay? So if they intersect all at one point, would be this one, when they intersect all at one point. So to determine this, we have to enter the Cartesian equations for all the three lines into the GC, for all the three lines into the GC using the simultaneous equation, the three planes. Okay, so we enter the Cartesian equations for all three planes into the GC using polysimult, so the simultaneous equation solver. So if there is only one solution, then we know that the three planes only intersect at one point. If they intersect at a line, then the solution set will be in the form of the last coordinate. So it might look something like just now when we have this, where everything is in the form of x3, but we can change the value of x3 to get different sets of xyz. So with something like this always defines a line. So the set of all these, which we call the locus, will define the entire line. And if the three planes don't intersect at all, so something like this, then no solutions will be shown. Okay, so but do realize that three planes are a lot less common than two planes questions, so you don't have to worry about it. So that's it. We have completed the interactions between all the kinds of interactions that can happen in 3D vectors. So to see how this plays out, let's look at the following sample question. So with just now type 2 question, we see that the first question here, right, we have a line and we have a plane. So this is type E, line and plane. Here we have line and plane, so line plane. Then this is shortest distance from a point to a plane, which we covered earlier, right? Point and plane. Give a reason why two planes intersect in a line. So this is plane and plane, what we just talked about. And this is explain why point P lies on a line L where two planes meet. So this can be classified as point line or point plane. So we do realize that this kind of application questions falls into one of these 6 categories. So knowing the special techniques to ace each of these 6 categories will be sufficient to do well and ace this topic in the H2 examination. So we've come to the end of our crash course on vectors. Thank you so much for listening, and I hope you've understood not only the key elements and the key concepts in vectors, but also how to apply them in solving problems with special strategies in vectors. Goodbye, and stay tuned for our next video.